All right. Okay. Are there any questions before we get started? A quick scheduling note. I will be wrapping up today's class a few minutes early. I get to go get my first 2 shots to public health. So very grateful for that. So over 50. So what I want to do is give you an overview of the 3rd unit, which looks at equilibrium systems, specifically in aqueous solutions. Why? Because these are critical to understanding living systems. And so there are 4 types of equilibrium. I'll say them currently, and I'll confirm in detail what's right on here. We're going to talk about weak acids. We're going to talk about weak bases. Talk about a combination of the 2 called a buffer. And we'll talk about solubility, how things dissolve. So those are 4 aqueous equilibrium systems. Now, in particular, I want to emphasize the biological importance of the first 3, weak acids, weak bases, and buffers. And it largely has to do with these big molecules called proteins. These proteins are long chains of amino acids. These amino acids, some of them have weak acid, weak base properties. And the behavior of the weak acid or weak base and an amino acid helps to influence the structure of the amino acid chain of the protein that results. So the shape of a protein is very much dependent on what's going on in that aqueous solution. So a protein determines what it can do. So a classic example are the 2 proteins, myosin and actin, responsible for muscle contraction. If you change the pH, the shape of the myosin actin fibers change, or the ratcheting motion that results in muscle contraction doesn't happen nearly as effectively. That's what we talk about feeling the burn. If you overexerted a muscle, it's not getting enough oxygen. Lactic acid builds up, changes the acid concentration, and then the muscle doesn't ratchet up. Its shape is changed. Now, if you're fortunate enough to go on in your educational career and take a biochemistry course, I sure hope you do, because this weak acid, weak base buffer stuff is bread and butter to biochemistry. It determines the shape of proteins. The shape of protein determines its function. And all of the chemical reactions that are present in your body and my body are catalyzed. The rates are accelerated by proteins called enzymes. Their effectiveness depends on what's going on with their weak acids. Now I feel a little bad because off in the corners it's the solubility equilibrium, and all of a sudden, they're feeling all guilty because everybody's all excited about weak acids and weak bases. Solubility equilibria have a role, but it tends to be more in terms of environmental chemistry. So how certain things dissolve and get into aqueous systems. And then those materials have impacts on biological systems. But my heart's set on biochemistry. So protein chemistry is critically dependent on weak acids and weak bases. Now, from the standpoint of the course, the 3rd exam, what you're going to enjoy is the fact that weak acids, weak bases, buffers, it's almost all the exact same math. The only question is which substances do you have a lot of, which substances do you not have a lot of, and which thing are we keeping track of in this system. Solubility systems are a little bit different. They look a little bit different. They still follow the same general math of equilibrium systems. We're going to use the Rice table over and over and over again. I'll show you some math shortcuts so you don't have to keep going to Desmos, but Desmos will always be available. Questions about the big picture? Pretty soft with weak acids.
So our generic formula for any kind of acid is going to be HA. What an acid does is donate hydrogen. Think about the substance's chemical structure. One hydrogen, or possibly more than one hydrogen, that's involved in a highly polarized bond that is electron deficient. And so the hydrogen looks for other sources of electrons. Now, because we're talking about aqueous equilibria, the key molecule in all of these is going to be water. In the case of weak acid, what's happening is the electron pairs on the oxygen are actually more available than the electron pairs from the rest of the acid molecule, just represented generically by A. You don't have to know what that A is, but and we'll go through a whole bunch of different examples of what might be a weak acid. But using an arrow, what we're saying is the electrons from the oxygen are actually plucking off the hydrogen from the weak acid. Now, the forward direction, what happens is water picks up that third hydrogen to make what's called a hydronium ion. And you're left over with the rest of the acid molecule, which now has negative charge. This is aqueous. This is aqueous. This is a pure liquid. This is aqueous. In the reverse direction, what happens is that A minus still has an extra pair of electrons, and it grabs the hydrogen back and forms the original weak acid. One molecule. Now there is a balance established between the forward reaction rate and the reverse reaction rate. Now we could write out what's called a KC for the system. So we write out a KC for the system. All the concentrations. Hydronium ion, it's the conjugate, divided by original weak acid, water. The water's concentration is large and not going to change substantially. So it's considered a constant included in the equilibrium constant value. And we change the subscript to indicate we're specifically talking about an acid equilibrium. So we just keep track of the hydronium ion, A minus, HA. Just a quick bit of vocabulary, the H3O plus we refer to as a hydronium ion. The A minus is referred to as the conjugate for connected, conjugate base. And we'll talk about its behavior as a base in a few minutes. The reason why we call it a base is because it's picking up a hydrogen. So we're going to set up our rice table. I'm going to screw down just a little bit because I put those words underneath. So let's say this initial concentration is 10 molar. And I have to keep track of water, pure liquid. And we're going to assume that there are no hydronium ions, no conjugate base ions initially. As we approach equilibrium, we're going to use up a little bit of the weak acid, make a little bit of hydronium, make a little bit of the conjugate base. Copy the expression. So we have to Ka value. Unfortunately, there's a table for that.
Now, on the shared side, you guys have already experimentally determined Ka value. Gillette, I can't remember the lab schedule, but they're supposed to be working on that. And you haven't done that already. So this is the Ka table from the textbook. That's what it does, is list a bunch of different weak acids. And then off to the right, it provides a Ka value. It also provides a mathematical equivalent called pKa value. We'll talk about that. You can see that most of the Ka values are 10 to the negative somethingth. Some are really small, like 10 to the negative 12. Others are a little bit bigger. There's a 10 to the negative 3 there. So the idea is we would know something about this weak acid, which weak acid is, go and look up its Ka value. Let's call it 1 times 10 to the negative 4. So we look up the Ka value. Now at this point, this is where Desmos would come in. You could go ahead and plug this in Desmos and solve for X. But let me just quick little trick. If I look at this concentration and I look at the Ka value, and there's a big difference between them, where the Ka value is much, much smaller than the acid's concentration. What that means is that there's going to be very little for reaction. The K value is very small, doesn't favor the products. If that K value is small and you're not going to get a lot of product, that means addition and subtraction terms are insignificant. What that means is I can treat this subtraction term pretty much like 0. That's not the problem, becomes a lot easier. I get x squared over 0.1 equals 1 times 10 to the negative 4th. X equals the square root of 1 times 10 to the negative 4th. Now, if you plug this in Desmos, you will see a difference in like third or fourth digit. But typically that's beyond our ability to measure the original acid anyway.
For the square root of 1 times 10 to the 5th, we should choose a different Ka to make the math easier. So I can square root 5. 0, 0, 3, 1, 6.
That would be the hydrogen or hydronium concentration. Now, as a technical matter, chemists will write out H3O plus because it's a more correct description of what a hydrogen ion is going to do in solution. But as a shorthand, quick note, we'll write H plus, a hydrogen ion. That hydronium ion concentration can change wildly depending on what's going on in the solution. So over several orders of magnitude. So chemists agreed to another description of the hydrogen concentration called pH. It's the negative log of the hydronium concentration. In this case, that would be the negative log of 0.00316.
Six.
pH is 2.5. Questions?
Is that concentration for A minus too? Or is it just?
It's also the concentration for A minus. This question, let me repeat the question, see if I got it. So is that point, are you asking, is that 0.00316 also the A minus concentration? It is. But it turns out in terms of things that happen in solution, is that hydrogen ion is really important to keep track of because it does a lot more, it's a lot more active. So chemists tend to obsess over the hydrogen concentration, so that's what pH does. There are times where we're interested in that concentration and we've solved for it. But there's no alternate description.
you see that?
But you have the pH, not the K. How would you find the K? Excellent question, Alexis. Thank you. So Alexis, I'm gonna kind of go through it quickly because this is more of an overview day, but I want to respect it. Great question. We'll go over this again in a couple of days, but the gist of it is this. If you know what the pH is, pH is negative log of the hydronium concentration. You can figure out what the hydronium concentration is by undoing the logarithm and the negative pH. So I would take the 2.5, so that's the negative x1, which would get me back to the concentration, 0.00316. So the idea is if I know that concentration, I also know the conjugate concentration, the conjugate base, because it is a one-to-one relationship. But Alexis, the other piece of information I have to give you is I have to tell you, hey, here was the original concentration of the acid. So at this point, we know the hydrogen concentration. And because it's a one-to-one relationship, we know conjugate concentration. But I would also have to tell you what the weak acid concentration is. So let's say it's 0.2 molar instead. I would count that and give you the K. And that's one way to approach a K value experimentally. But I have to give you a pH value and I have to give you the acid concentration. So you have a sense of how much ionization you got, how much hydrogen ions they produce relative to the original acid concentration. Other questions? Weak bases. Represent a weak base with letter B. Depending on the nature of the molecule, you might have a negative charge or you just have a pair of electrons. In the presence of water, the base has enough electron density to pull hydrogen off of water, not give it to water, but to pull it off of water. So in the forward direction, water becomes a hydroxide ion. Base now takes on a positive charge. Now, the other possibility is the base came in with a negative charge, picks off the hydrogen, the base becomes neutral, hydroxide develops a negative charge. In the reverse direction, that hydroxide ion pulls the hydrogen back off. And now we get back to water and the original base. But now look at the step back and look at the big picture here. We have water here picking up a hydrogen. We have water here giving up a hydrogen. And this speaks to one of the unique properties of water, that it itself is both an acid and a base. It can give up a hydrogen in certain situations, pick up a hydrogen in other situations. There aren't a lot of molecules that do that. Certainly not any that serve as such a universal solid for salt like this. We refer to this as the hydroxide ion. That one you should know already. And this is what we call the conjugate acid. So it's connected to the base, but it itself has a tendency to give up hydrogen, doesn't it? Same thing, we can do the rice table, RICE. Let's say its initial concentration is 0.1, we don't keep track of water, we're going to assume no hydroxide or conjugate acid initially. We're going to heat up a little bit, make a little bit, make a little bit. So our KB expression omits the water. Products of reactants. So I'm hoping you see the math is nearly identical. What's different is which way is the hydrogen going? Who's picking up the hydrogen, who's dropping off the hydrogen? Now, we need the equilibrium constant. And fortunately, there's a table for that.
So after the weak acid, weak base table, after the weak acid table, you turn the page, there's more weak acids, and then there's a table of weak bases. For example, you got this ammonia. This ammonia picks up a hydrogen off of water. You get the ammonium ion and the hydroxide ion. It doesn't matter which one we write first. I'm writing the hydroxide ion here, but it doesn't matter if they go first or second. And there's a K value for it. I'll round that off to 1.8 times 10^-95.
So I should point out, for example, 3, all these tables will be provided for you.
If you want to use your textbook, you can have it. There's the appendices are all in a hard copy available. If you'd like a hard copy, make sure you send me a note. Gillette folks, I can send you a digital PDF. If you want, it's in the back of the book, whatever's easiest for you.
So again, at this point, we would drop this over Desmos, or we would take advantage of the fact that if the K value, K or KB, doesn't matter. If that K value is really small relative to the concentration, and our kind of guideline is about a factor of 1,000. So if the K value is a factor of 1,000 smaller than the concentration, it's pretty reasonable to ignore emission subtraction terms. Now, again, you guys, I'm super happy for you guys because you got decimals. I know Alexis, I feel so bad. Alexis is trying to take her exam and decimals like went offline. I mean, no, and I'm like, oh no, decimals. You've always got the access. You can use decimals to solve this stuff. The reason why I'm sharing this in shortcut with you is because it is actually faster than typing in decimals and zooming in on the quadratic to figure out where it crosses the axis. So I'm going to do 2 steps in one. I'm going to move the 0.1 over. I'm going to take the square root. X is equal to the square root of 1.8. -6.
Square root.
Second exponent equals 6.
0.00134.
Now, I just want to verify this for you up front. Fire up decimals here. We've got X.
X times X. And
So what I'm doing is I'm just taking that equation into decimals. I just wanted to verify it for you that print our data. .00133325. So the approximated answer I get is 0.00134 versus the explicit Desmos answer 0.00133. And that third decimal place is well beyond our certainty about the original concentration anyway. So that's what we would call a reasonable approximation. And it would be certainly acceptable on the scale of 3. But you guys have access to Desmos. Feel free to use Desmos, but we use these shortcuts because they get us reasonable answers. Now, the answer that we have here, this is the hydroxide concentration. So we can take the negative log of that number, negative log of 0.00134, and get a value.
Negative log 0.00134.
I get an answer, 2.87. But that is no longer what chemists refer to as the pH. That's what we would refer to as the pOH. Because the letter P here is a mathematical tool that refers to how many powers of 10 essentially. And then you put the letters representing the chemical substance that you would figure out the powers of it, the concentration. So pH describes the hydrogen concentration. pOH describes the hydroxide concentration. And the catch is this: as an arbitrary choice, chemists have chosen to follow the hydrogen, even when describing basic solutions. So the way we get around that is to realize there's a mathematical connection between these two, that the pH plus the pOH has to add up to 14. The logarithmic description of hydrogen concentration and the logarithmic description of hydroxide concentration are tied together when you're in aqueous solutions. Why? Because of water. Because water is both an acid and a base, it will always tie together the hydrogen concentration and hydroxide concentrations. So if I know the pOH is 2.87, then I know the pH has to be 11.13. And notice that pH value is a very different number than the pH value we calculated for weak acid. Going back to Alexis's question earlier, if we don't have the KB, we can figure out what the KB is, but we have to have information about the hydroxide concentration and information about the original base concentration. Questions? Yeah, I'm clear what's on the board. Is there any questions? So buffers simply mean you've got a weak acid and a weak base together. Now, typically, the weak acid and the weak base are the same substance. You have a weak acid and its conjugate base, or you have a weak base and its conjugate acid. Let me give you two specific examples. So we have the weak acid, acetic acid. Or you have the weak base, ammonia. Reaction, initial change, equilibrium. So So in the buffer, you would have an initial concentration for your weak acid. But you would also have an initial concentration for your weak base. Now, there's a practical detail, and that is I cannot go to my stock room and get a bottle of this combination by itself. Anything that's ionic, you can't get just the negative ion or just the positive ion in a stable form in a bottle on a shelf. So this would come into the form with a counter ion. Usually a sodium ion or potassium ion. Now the name for this stuff is called the acetate ion. And this would be sodium acetate. But the idea of a buffer is you have a weak acid and you add some of the conjugate base. There's the initial concentration. We assume there's no hydronium initially. If there's none of the hydronium initially, we're going to use up some of the acetic acid to make a little bit of hydronium and a little bit of the acid. Now, what's nice here is that little trick about ignoring addition and subtraction terms. That becomes really helpful here. If we read our K expression, products, reactants, where acetic acid official Ka is 1.76 times 10 to the 5. So again, you could take this to Desmos, perfectly fine, but I'm going to assume addition and subtraction terms are negligible because that Ka is pretty small. And now the math gets really easy. X equals 1.76 times 10 to the 5 times 0.1 divided by 0.2, so essentially dividing by half. 1.76 second exponent negative 5 divided by 2. I could take the negative log of this. Point 3.05, 3.06. Now what we notice is the pH here is going to be a higher value than the corresponding weak acid by itself. Because what we're doing is employing Le Chatelier's principle. We're adding one of the products. By adding one of the products, the system's going to try to use that up. And so it's going to try to use up any hydronium ion. It's going to be less available hydrogen ions. That means your pH. If you get a smaller and smaller number here, the pH is going to get higher and higher, indicating a less acidic solution. But more importantly, what this buffer does, we'll get into this in detail in a couple of days. If I add additional sources of hydrogen ion, this acid ion can sponge it up. Or if I add something like a base, it's going to try to, if I add something like a base, there's a weak acid available to use that up. And so what buffers do is they resist changes in pH. On the base side, math is identical. We have an initial concentration of ammonia, an initial concentration of the ammonium ion. Again, I can't get a bottle of just the ammonium ion, so it's probably something like ammonium chloride. You drop that into water, and the ammonium ion from the ammonium chloride becomes part of the system. It's available. Chemists refer to this as the common ion effect. if you have an ion that you're adding that is common to that equilibrium, it's going to have an impact on the equilibrium. Doesn't matter what the source is. Doesn't matter where I get the ammonium ion. If I get it into the solution, it's going to start playing with this equilibrium system. Remember, don't keep track of the water. We're assuming no hydroxide initially. So KB 0.3 plus X times X minus X. That's equal to for ammonia, that's 1.76 times 10^5. Addition and subtraction terms go to 0 because the K is much smaller than the concentrations involved. So X 1.76 times 10^5 divided by 3. So that's times 0.1 divided by 0.3, which is 1/3. 1.76 second exponent -5 divided by 3. Five zeros, 5.8. 7 times 10 to the -6. So I can take the negative log. I get the 5.23. But remember, that's the POH because it's describing the hydroxide concentration. H plus POH equals 14. This is 5.23. This has got to be 9.6. Is that 8.77? That's 1. Yeah, 8.77. Now, if you go back to your previous notes, you'll see that ammonia by itself had a higher pH. Why does it have a higher pH? Because you didn't add this conjugate acid. By adding this conjugate acid, you made more hydrogen ions available. That reverse reaction is providing additional hydrogen ions lowers the pH. 8.77. Now let me emphasize, by the end of, we're going to wrap up here in a couple minutes. By the end of today, you are not supposed to be able to do all these by yourself. I'm just saying, here's where we're going. We're going to start off, I see on Monday, we're going to do weak acids and talk about weak acids. And then Wednesday, we'll talk about weak bases. We'll stop a little bit of review on those guys. Next week, we'll do buffers. Finally, is there anything on this board that you want to go over before I erase it? Bases are always POH, acids are pH. Yeah, that's a pretty good summary. You can work out the pH in a basic solution. It's always going to be closer to the 14 end of the pH scale. We'll talk about the pH scale in detail. Let's see on Monday. But the larger concentration is going to be hydroxide. Carbonate, otherwise known as marble or limestone, in the presence of water, dissolve into its calcium ions and its carbonate ions. But at a certain point, enough ions dissolve So their attractive forces become sufficient to bring them back together. There's going to be equilibrium established between the dissolving process and the precipitation process. So we can write what's called a KSP. Solubility property. And it looks a little odd because solids have a concentration that do not change. We do not include them. So the KSP is just calcium ions concentration, carbonate ion concentration. We can set up a rice table. We're not going to bother with the calcium carbonate, it's a solid, as long as it's present. We're going to assume that no ions dissolve initially, but that a small amount do over time. So our KSP, which is the calcium ion concentration, carbonate ion concentration. X times X. Now there's a table for that one too. Solubility product constants. It's listed by the cation. So here's calcium, and then carbonate's the first one listed. It provides the equilibrium equation. 2.8 times 10 to the 9. You'll notice these KSP values are typically much smaller than our KAs or KBs. Now, the nice part about solubilities is that there's no alternate description that chemists came up with. Once we solve for X, that is the concentration of the ions as solution.
Square root of
Second exponent.
5.3 times 10 raised to 5.
So that would be the concentration of calcium ion, that would be the concentration of carbonate ion. And since the calcium carbonate are both 1-to-1 with the original calcium carbonate, we would also say that's the solubility of the calcium carbonate. Now, one of the challenges you run into in solubility systems is that there are several combinations where you have calcium fluoride. So that's going to be an equilibrium with calcium ions and 2 fluoride ions. That 2 becomes an issue. You've got to keep track of it. It's going to show up both in the rice table as twice as many ions. Then it's going to show up in the equilibrium expression. So you got the concentration description, but then the equilibrium expression has that square term. It shows up twice. Now, its general rule is KSP provides a quick sense of how soluble the substance is. But if you're comparing one substance to another, you have to make sure you have the same ion ratio. I mean, you got to have a 1-to-1 combo. You can't compare a 1-to-1 combo to a 1-to-2 combo without actually working out what the actual solubility is. The KSP by itself isn't going to get you. Just a quick note, if you've ever gotten a chance to be in a cave, in stalactites, stalagmites, it's all calcium carbonate equilibrium. Every stalactite you see, every stalagmite you see, those are calcium carbonate ions. There's an equilibrium that allows it to dissolve in one location and reprecipitate another, depending on the ambient concentration.
talk more about calcium carbonate in a couple days for sure.
My questions. Gases, bases, buffers, and solubility. We are going to wrap up early. Sharon, folks, I'll see you for lab. Everybody, I'll see you next Monday. If you would make sure read through the chapter, next chapter.
We talk about the posters.
Oh yeah. So real quick, there are actually two. For the Sheridan folks, there are two separate posters because we've got a lab component. For everybody in the course, you have to do a just general chemistry topic poster, and so that is any topic related to chemistry that you want to do a poster on. Poster format is variable. Got a kind of default format you can use. Gillette. It's up to you if you want to do something digital. Yeah, you have to create a poster for class. Yeah. You don't have to present the poster. I'm not going to do a poster session. But you have to submit the poster. So,
Question.
Yeah, did you ever get the pie nice guy?
So I tried it on my own. It's time out for a second. Are there questions about the
Sorry.
what kind of questions you saw about the poster?
I just wasn't sure what, like, if it was different than our lab or not.
Yeah, so Sheridan, you guys have a poster.
For your independent lab work, but you also have, everybody has a chemistry topic poster. It's toward the end of the semester. You double check. Wednesday, April 7th.
And we can work with the partner on those.
Yeah, if you want to work with somebody else on the topic poster, if you need help brainstorming the topics, make sure you send it out. We'll get on a phone call or as well. Oh, thanks for patience. So I tried to fire it up on my computer and was having trouble. You have to know how to type stuff in, not a user interface. So I've got a meeting scheduled here.
IT teachers. It's really
Thank you very much. You have example posters to get an idea of what, yes, I can send, I've got some hard copy posters, send it over here, and I'll set up. I send them to you.
I'm gonna go grab a coffee.